Introducing Portraits and Ideas. I'm Erlen Gal presenting interviews to inspire and perhaps unveil something new in the realm of ideas. I would like to introduce you to you today, Professor Hakan Bagci, and we would like to ask you, what is your title and position at KAUST?
I'm an assistant professor of electrical engineering under the division of physical sciences and engineering. I started on August 1st in 2009.
Okay, just 1 minute. That's fine. Why did you decide to come to KAUST?
KAUST, I believe, is one of the unique places where you can do your research without worrying about the financial aspects of the academia. In Western universities, in a typical Western university, to do your research, you need to get funding from external resources like research agencies, sometimes armies and air forces and agencies like this. But KAUST is an internally funded university where you really don't need to worry about funding problems. So you can really try to do groundbreaking research without worrying about the other aspects.
What advice would you give to youth in Saudi Arabia to promote their interest in pursuing science careers?
I think they should start with really working hard on their classes during the university. So without having a fundamental, without covering the fundamental basics, you cannot basically be successful in doing research. So the first step in being a successful researcher is to start working on your classes. Once you have the fundamental knowledge, I think you should try to improve yourself by working with people who have experience in the field you are interested in. And we have many of these people here at KAUST. So.
You talk about the basics. What courses would you single out as being key for them to work on?
I guess if you are going for a degree, if you want to do research in an engineering field, the fundamental classes are math classes. First, I will start with math classes, and then mathematics classes, and then you should go maybe some fundamental physics classes, and then you can start building up based on your degree. If you're a mechanical engineer, you want to take some mechanical engineering classes. And in electrical engineering, it's typically a combination of computer science and some spatial engineering, electrical engineering classes.
Mm-hmm. So obviously that's pretty advanced along when someone is in high school, for example. What would you advise for, say, students at a much younger age? I mean, to in terms of their preparation early on.
Okay, if you start at a younger age, I think the analytical thinking ability is the most important one if you want to go for a scientific career in engineering. Mm-hmm. Other than that, again, the solid mathematics background is important.
In other words, pursue math relentlessly. And what about this analytical thinking? How do you define that?
I think you can define it as like problem solving capability. Mm-hmm. So for a given problem at hand, you should be able to come up with creative solutions to that problem. Mm-hmm. So I think that is really one of the fundamental fundamental.
So what I'm hearing from you is problems are something to cherish and enjoy. Don't run away from them. Even when they're tough, because it teaches you how to think. You know.
Yeah, actually, maybe the second most important thing is to be. I mean, it's never give up.
Yeah.
Whenever you face a challenge, you should try to basically. You should never stop trying to solve it. That's the. I think that's one of.
That was your strategy in school, obviously, to never give up.
Yes, I mean PhD is a long road. I mean, you start in high school by choosing mathematics and science electives. That is 4 years, and then you go to university. That is 4 or 5 years in addition, and then you go for a master's, which is 2 years. And then you do your PhD, which is 4 or 5 years. So I think the whole thing adds up to like 15 years of education before you become an expert in your field. So it's really, you should never give up.
That's right. That's right. It's a long, how should we say, journey.
Yeah, long journey.
If you will. How did you reach the position you're in today in your career? Namely, you outline and explain the milestones that in your educational advancement to reach the PhD.
I think my high school education was somehow important because high school was the place where I understand the importance of education. I mean, my teachers, they were always emphasizing the importance of higher education, like university, even masters at that time, and PhD. So that was the time when I decided to pursue a career in academia. And I worked hard, obviously, even in high school, to get to a really prestigious university in Turkey.
Which university was that?
It's Bilkent. It's in Ankara.
And what makes that university prestigious? Spell that name again.
Bilkent.
Bilkent.
Yes. Bilkent.
Okay.
First of all of the faculty that work at Bilkent, they all had their educations in United States. So they are really the people who are in like the top of their field. So I think that's one of the most important features of Bilkent. And the other one is we have this university entrance exam in Turkey. So Bilkent accepts electrical engineering department at Bilkent recruits students from the I think top 200 out of 2 million people. So in order to get to that top 200, you really need to work hard during your high school. So.
Yeah, well, obviously you you made the cut at a very low level. What advice would you give to students who might be preparing for exams? That was obviously a tough challenge for you, competing against 2 million students.
I mean, as we discussed this like a couple of minutes ago, the main idea is to never give up. Mm-hmm. You should always work hard. I mean, there might be some like disappointing factors. Sometimes you might fail, you might get a bad grade from a class, but you should never give up, and then you should really, you should really try to improve yourself in the places where you're not good at. You know?
Okay, now that's general, but obviously when you were preparing for your exams, you made some special strategy that you sort of developed for your preparation. What did you do? You spent a couple of hours every day for several months on solving problems. What kind of technique did you use to prepare?
Actually, the exam has a really specific structure in Turkey. So it's, I think 200 questions. You need to solve 200 multiple choice questions in 3 hours. So it's actually less than a minute per question. So the key is basically the repetition. So you need to solve lots of questions, similar questions beforehand to be successful at this exam. So basically you start like 2 years ahead of time, and basically first you cover the fundamentals again in classes, and then once that is done, you start solving questions. You start solving.
Was it all math, or did they had some other language questions?
We don't have language questions. The exam had four main parts: math, sciences, like physics, I think chemistry and biology.
Mm-hmm.
And also there was also social sciences like psychology and that kind of things.
Sure.
Based on the school you're applying, the weight of these sections are different.
That's right.
Yeah.
That's right. Your particular school obviously put the weight on the math and the science section.
Yeah, exactly. Yes.
Exactly.
Yeah.
So then, what made you decide to get a Ph.D.? I mean, that was a big leap from just going to get your bachelor's at Bilkent.
Actually, my professors at Bilkent, I think they have a role in this. I mean, when I first started, I was really impressed with their level of knowledge, the level of experience in their fields. So I always wanted to be like one of them. So that was the main, the driving point was that. And after I started PhD, I really like what I was doing. So I continued to until I finished it.
So in that regard, would you be very keen to advise students who might consider science careers to actually go all the way to the PhD rather than stopping with a master's, for example?
I think the logical thing would be like test yourself. Like, okay, you get your degree from undergrad, so you really test yourself and to see if you really like what you are doing. And if you do, I would strongly suggest you to like continue. Try to get a master's in the same field if you really like it. And then after master's, test it again. Do you really like what you are doing? And if you do, I would really suggest you to continue PhD. I guess that's the key point.
Mm-hmm. In your work in electrical engineering, what would be the relative advantage of hard work to accomplish your goals versus high levels of intelligence?
I think it's really an equal mixture. High level of intelligence, it's a big plus, but it's not everything. I mean, lots of things can be accomplished without being a genius. I think it's,
sure.
To be honest, I think that's
sure.
the way to put it. Of course, being a genius, if you're a genius, that's a really big plus. You can do lots of things probably much easier than other people. But I think the main thing is really the hard work. So you should really put your heart onto the thing and then never give up and work.
The reason I ask that question is because a lot of students might feel that they are not necessarily in the top 10% of their class, and they feel that this is a lifelong handicap. But in fact, they may be able to overcome that difference with working hard and pursuing things with this persistence.
Yeah, definitely. Yeah. I mean, I think persistency is the. It has a heavier weight than the intelligence level. Yeah, definitely.
Mm-hmm. When did you decide to become a scientist and a researcher? At what point in your career? What was that spark? That
spark was actually, I think it was in my third year in college. I really decided to spend some time with one of the professors by doing some undergrad research with him. And then I was really impressed what he was doing. He was doing research in electromagnetics, and I really started to like what I was doing with him. I was basically, initially I was helping him with some, actually I would say easy stuff. But as time progressed, I also started to get more involved with his projects, and so I really liked it. And then at that point, I decided to go for a career in academia.
For our students out there, how would you define electromagnetics, and what made that exciting for you?
Electromagnetics is it involves lots of math. I think that was really what attracted me to the field. And to be specific, I'm doing research in computational, yeah. So it also involves lots of programming skills. That's also one of the things I like doing and I'm good at. So that was really the combination of the math, the nice mixture of mathematics and the programming was basically what attracted me.
Okay, so those were the key kind of tools and skills that you learned, and they were fit right in with advancing your knowledge of electromagnetics. But go back to just some basic discussion of electromagnetism and what does that mean? What are the implications for a young scientist out there who might be interested in electromagnetics?
Electromagnetics in general is basically it's used to define the relation between magnetic fields and electric fields. In the modern technology these days, these are important to like to understand the relation between the fields is important to understand how some systems work. Like for example, the wireless communication between a cell phone and the base station. These are really the fundamentals. I mean, when you, for example, understand how the propagation occurs, how the wave propagation happens between the wireless antenna and the cell phone and the base station, I think that's what the electromagnetic that's being taught at universities right now.
Mm-hmm.
The knowledge you gain in an electromagnetics class basically will let you to design antennas, for example. This might include different types of antennas like microstrip antennas, cell phone antennas, dipole antennas that are used for broadcasting radio signals, for example. So it has really many application areas.
Mm-hmm. So if we go back to our original ideas on electromagnetics, we think about Maxwell's equations and so on. How could someone in the 1800s, develop this kind of advanced understanding of electromagnetism when it's kind of invisible? You don't see it. Did the math come before the actual awareness of the phenomenon in nature, or they had other things to measure this phenomenon?
I think it all started with the physical observations.
Mm-hmm.
I mean, before the actual formulation of the Maxwell equations,
Mm-hmm.
I think it was Hertz who first managed to propagate waves from, I think, to Europe to US. I think this was around the 1800s.
Mm-hmm.
So I guess the scientists first, they observed the physical phenomena, and then they'll try to develop equations that will model this physical phenomena mathematically.
And that kind of procedure is carrying on to today, where we as scientists will look at physical phenomena and we maybe more with newer instrumentation and so on, and then we try to model that mathematically. That's a continuous process, isn't it?
Yes, I mean right now one of the, I think it's called enabling sciences, is developing, for example, let's say some simulation tools for imitating certain physical phenomena. I mean, let's, as an example, let's take the Maxwell equations. So you have the physical phenomena, and you have a mathematical model that defines the relations between parameters in this physical phenomena. and then you basically, using these mathematical models, mathematical equations, you try to imitate the physical phenomenon on a computer, and then develop a simulation tool, which will be, for example, useful in designing an antenna later.
Mm-hmm. Mm-hmm. So that gives us a powerful tool, modern computers, where you can actually simulate nature on the computer, and
Yes.
and you don't have to necessarily have the actual physical phenomena occurring.
Yes.
Yeah. So does KAUST offer advantages in that regard? Because we have one of the leading supercomputers for a university, I think, at the moment, number 2.
In academia.
Academia. So would that give you particular advantages in modeling?
Yes, of course. I mean, when you have larger computational resources like the one we have here, Shaheen, which is I think the fastest in Middle East and second in academia, second fastest in academia, you can always model larger problems. And these kind of facilities, they are typically useful for all scientists in all areas of science, from climate modeling to, for example, like in electrical engineering, people in electrical engineering. So, I mean, it basically helps the scientists here at KAUST to always have that cutting edge difference when compared to the other universities.
What was the childhood stimulus that occurred when you were growing up that made you interested in science?
I mean, I don't recall like a spark, but I always like reading, for example. I mean, in my spare time, like while I was not at school, I used to read like lots of encyclopedias, science encyclopedias. I was just, I just pick one of them and then I would read it like for hours maybe. I think that was the...
Did you go to the library to do this, or you had these books at home already?
I had some of them at home. Both of my parents are teachers, so they had lots of books.
Sure.
But I used to go to the library.
So you gravitated towards science books mainly?
Yes.
That was where your interests lie.
Yeah,
so were they science fiction or science fact?
I guess it started with science fiction. I used to like reading novels from Jules Verne.
Jules Verne, the classic science fiction writer, right?
And then, after you read these books, you get somehow stimulated about the whole science. And then I started to read the fact-based books like Encyclopedia Scientifica.
Sure. I mean, that's good encouragement for any student there who is interested in a career in science, is to really become widely read. And so you demonstrate that obviously gave you a lot of, how should we say, ideas that you got from your reading about various aspects of science, and led you in various directions, and then you ended up in electrical engineering. But certainly that wide spread of your reading habits was a major contributing factor.
Yes.
Mm-hmm.
I mean, I think reading is important regardless of what you are doing. I mean, it doesn't matter whether you are working in a social science like psychology, sociology, or something else, or in a scientific field like engineering. I think reading is one of
it's primary.
Yeah.
Absolutely. How much time daily did you spend learning the skills that helped you the most in school? And what would you consider those key skills?
I mean, the most important skill I have, I think, it's the analytical thinking ability. And that is something you can really gain by solving problems, math problems, science problems. I mean, these are not supposed to be really things that require creativity at first. You start with, even homework problems are important. I always try to complete my homeworks, for example, in math and science classes, and including the other ones too. I think that was the first step. and then you really gain the ability to think by yourself creatively.
Mhm.
But I think the starting point is really exercise, practice, solving lots of
Yeah.
problems.
We go back to that.
Yeah.
Repetition
Yeah,
in
exactly.
problem solving.
Yeah,
Just
yeah.
go through as many problems as you can.
Yeah, and then
Yeah.
you learn how to deal with more difficult problems, more
Sure,
challenging
sure.
problems. Yeah.
Sure. And how much time? I mean, obviously, when you were in primary school and then you went into high school later, and junior high and middle school, you give me the timelines in terms of, after school, how much hours you would spend a day, and then as you got into college, obviously it increased. So give me that step-by-step increase in hours.
High school, I think the classes were from like 8 to 4. And then I would say I would spend another 4 or 5 hours maybe in the evening and night to work on the classes. And
Was this motivated by the quantity of work the teacher gave you, or you were self-motivated to do that, whether it took you that amount of time to do it or not? In other words, I'm just curious as to what your study habits were.
I think I was doing some additional things too. I mean, it was not. I mean, that 4 or 5 hours was not just
Homework.
Was homework. Yeah, I was doing some additional reading and.
Did your parents encourage you to do that, or you had that sort of internal engine?
No, I think I was self-motivated.
Self-driven, self-motivated. Yeah. And do you think that habit has continued with you today?
Oh yeah, of course. I mean, actually, that is really one of the key factors in being successful at academia.
Right.
You need to be always self-motivated. You don't need to be.
Suppose you picked up a book and it had some information that was difficult for you to understand, and you were trying to learn it on your own. What would be your technique to try to break through that barrier of difficulty?
I would try to go like one level easier. If you are reading a book, probably you'll find some references in there where you can do a little bit probably easier reading. I'll basically would go back one step and then try to understand a simpler thing related to the same subject. And if it doesn't happen, you just go back one more step. I mean, that's really how the thing is built. And you go back till you understand something, and then you try to go forward. I guess
that's powerful. That's a powerful system. I mean, in other words, you just gradually
build up your knowledge.
Go down to the level in which you can begin to understand, and then work your way back up slowly.
Yeah, yes.
And that's a very interesting idea. Okay. What circumstances in your childhood contributed most to reaching the goals that you have accomplished so far?
I mean, I relatively had an easy childhood. I mean, I didn't have problems.
Mm-hmm.
My family was always understanding. They never gave me a hard time about anything, actually. And I guess I had the chance of being always getting into good schools. I think that was one of the important factors.
So these were schools that had competitive exams to get into, or they were schools that your parents knew about?
No, I started. I mean, I think my primary school was it was just a regular local school, and then there was this. Yeah, as you said, there was this entrance exam at the end to get into a better school. That I think that's how everything progressed. So I took that exam and I got into a better school, and the next step was basically to get into a good high school and college. Yeah.
So actually, I'm hearing also that you feel that your parents were important part of the circumstances of your childhood in terms of their influence as teachers on your sort of focus on education and
Yeah, I mean
Yeah,
that
yeah.
of course helped a lot. I mean they knew the importance of education. I think that's important. I mean even if I wanted to give up, probably I'm guessing they wouldn't let me. So I think
Yeah.
I think that's one of the important things.
That's a very good how should we say they use this expression, you picked a good two parents.
Yeah, I guess. Or they picked me. I don't know.
Exactly. Um, what circumstances did you see as the highest risk of not obtaining your goals when you were growing up? And if there were risks out there, how did you overcome those obstacles?
I guess the main problem could be financial problems, maybe.
Okay.
Typically, good schools are they are the private schools, and they cost a lot.
Right.
Actually, Bilkent is one of them, for example, college. But the thing is, if you are one of the top students, you can always get scholarships.
That's right.
I think that's a correct statement in all
Almost
parts of the world.
all possible. Exactly.
So my goal was basically always try to get into the top,
Mhm.
so that I will not have
Right.
any financial problems.
And you know, that's a very important point that many students even give up because they perceive the finances as being too challenging because their parents are poor and they don't have the means to support them. But I think you have just hit upon what the solution is. If the student takes the motivation to work harder, they can reach the scholarship level.
Yes.
And overcome this barrier,
Fine, yeah.
this perceived barrier through scholarships. I mean, and that happens in many countries around the world. I mean, to provide scholarships
yes,
for good students.
Yeah, the universities have their own scholarships typically. Sometimes some companies have scholarships for good students. Even some governments have government funded scholarships. They exist all over the world. So I don't see the financial side of the thing shouldn't be a problem. I think
Right.
as long as you work hard.
How would you describe your most effective methods of study and learning? Now, you mentioned one where if you had difficult material, you would just back off and go to a simpler material and just go back even several levels of simplicity. Now, as a successful student over the years, reaching a Ph.D. and so on, you obviously developed a system and a method and a procedure of studying and learning. What was your system?
I guess the first thing is the thing you just mentioned, and the second thing is it's really the repetition. You should practice a lot. You should try to solve as many problems as possible. You should put into the hours. That's also important. I mean, being persistent is one of the important things. I mean, I didn't have like a really specific system, but I never. I mean, I always stick to the main principles, like work hard, be persistent, and practice a lot. I guess
those three components were always a key thing. Like, okay, let's take an example. You're in a math book, and you reach a chapter where you find a lot of difficulty of dealing with the abstraction of this math, and it becomes something like a wall of that you can't get around or over. What do? How do you because the reason I ask that is because a lot of students, they'll reach that point in math, and it might be early on in math, and they give up and they say, math is not for me, I'm going to do something else. So people who become successful, you're a computational, you're applied math person, you model nature and electrical engineering through math, you obviously have reached a very advanced level of math. So I would assume that you had run into some barriers occasionally, and then you must have had a way of getting around that.
I mean, one thing was really was going back step by step, and then find a point where you can understand things, and then try to build upon that slowly. That was one thing, and the other thing is you should always ask for help. I mean, I'm thinking there is nothing to be embarrassed about it. You know, I mean, if you don't understand something, I mean, start with your friend. Just go ask him. Okay, I don't understand this. I mean, can you help me? Yeah. If he's not helpful, go to your teacher. I mean, this is really how it works. I mean, teachers are there to help people, so
sure.
To help their students, right?
That's right.
I guess
that's the key. I mean, in other words, it goes also back to what you said earlier to don't give up. Just use these techniques to get around, because even if your friend doesn't understand, then you say, okay, let's go to the teacher together and let's get this. Let's both get an understanding of this.
Yeah, until you can get the answer, you should just
keep trying.
Keep trying. Yeah.
Keep trying. Well, that's an interesting point about working on problems. I'll keep trying. They've done the study of students, and they found out that students from some countries would spend, say, an average of 5 to 30 minutes before they gave up. And then students in other countries end up spending 2 or 3 hours before they gave up. So there's a huge difference there in terms of the persistence question. And
it might be a cultural thing, I don't know. I'm guessing.
Sure.
But one other thing maybe I want to mention here is even trying, it's a process of learning too. I mean, you try something, maybe you cannot get the result you want to, but you'll definitely learn something else.
Sure.
So I think there's a huge difference between trying 30 minutes and 3 hours. So it's one of them is 6 times longer. So I'm guessing you'll have
something will happen in those other hours that you will learn. Even though you may end up failing in that particular problem.
Yes, but
failure is not really a failure. That's what you say.
I mean, you are gaining some other skills which will be useful some other place. So.
Exactly. And then I guess the other part of that, and when you do solve the problem, it's a good feeling about it. You know, you have a good sense of accomplishment.
Yes. I mean, if you solve a challenging problem, I mean, it really feels good. I mean, it's really difficult to describe that feeling, but it's satisfactory.
Have you had that, say, at a given point in your, say, Ph.D. thesis or something?
Yeah, I mean, finishing the Ph.D. after 4 years, that was first a relief.
Right.
And I mean, I was happy.
A big sense of accomplishment.
Yeah, exactly.
Yeah, absolutely. Okay, here's a general question. What are the most significant breakthroughs in science in general, not necessarily in electrical engineering, that you predict in the next 10 years, and in 25 years or 50 years?
I would say, speak in computational sciences. There were some algorithms developed recently in the last 10 years. Those enable the simulation of some certain physical phenomena in electrical engineering and particle physics. These basically accelerated the solution procedure. So these basically enabled the solution of larger problems when compared to 10 years ago. I think developments in this certain field, these algorithms, they will continue. And when this is combined with the increasing availability of computational resources like the computer cluster we have here, I think this will enable the solution of big impact problems.
What do you consider big impact problems? Right
now I cannot think of anything like that, but in the simulation, in the enabling sciences, typically almost all fields can benefit from these kind of developments in computational science.
So an example of that, for example, if they can simulate on a computer the Big Bang, that is a powerful tool to study the Big Bang. You know,
I think that
yeah.
might be important. One other thing might be maybe, for example, modeling the global warming effects.
Climate.
Yeah, climate
Yeah.
modeling. I think that will be useful in understanding what has happened so far, and what we can do to prevent global warming.
Although there's a pattern in global climate in terms of ocean currents and atmospheric movements and seasons and so on. When you get to some of the details of that, it becomes a kind of, for lack of a better term, chaos. You know? So we can actually mathematically model chaos?
I guess so. I mean, how you start that modeling is basically having some approximations and then try to simplify the phenomena. And you develop a model, you try to check the accuracy of that model, you try to validate that model. I think once it is, you think that it's good enough, you stop, but typically it's not. So you try to develop by increasing the complexity of your model. And right now, what happens is you basically either don't have the computational power to do that, or you don't have enough time in terms of, for example, CPU time. So you have to wait thousands of years to get the simulation result. So the main issue is really, I think increasing the complexity is not the problem, but having some fast solution is really the key problem.
So you are suggesting that as we get much more powerful computing,
yes,
power, we can really go after some really complex natural phenomena.
Yes.
As Moore's law become more manifest as things get smaller and more powerful.
Yes.
Yeah. What would be the most important scientific problems facing the world over the next 15 years, and would you have any methods that you would think to solve them, you know, using your imagination, which is considerable?
Yeah, I think global warming is one of them. So mathematical modeling is required, rigorous mathematical modeling is required to solve that problem, in addition to the computational resources. That might be one of the important problems. The other problem is maybe might be somehow establishing a network to distribute equally the resources of world resources like food, water. I think that's one of the important things.
Because in establishing this network, you're suggesting that we may have some of these resources, but they are not distributed
Yes.
evenly, if you will, around to the places where they are in great
I
need.
mean, that establishing that network has, of course, some social problems too, but mainly designing such a thing might also be like a big science project.
Well, even beyond the network, it would be also important to increase food production, increase water availability.
Yes.
So that's going to obviously require a lot of science advances to do that.
I mean, the first thing that comes to my mind is, for example, detection of water resources. That you can use again some modeling techniques and simulation tools for that purpose.
Go ahead. Yeah, I was going to ask you. You've actually mentioned that quite often. The concept of modeling and using mathematics to model. Okay, we have a problem, and we model it. Why does modeling help us solve that problem or come up with an answer?
Modeling is really the imitation of a physical phenomena. So what you do is you observe a physical phenomena, and for example, you cannot predict what will happen when you change certain parameters, for example. To give you an example, for example, if the ocean temperature increases, say 2 degrees, you cannot predict, without modeling, you cannot predict what will happen, for example, in polar soft Earth, you know. But if you can come up with a modeling, mathematical model, which will basically rigorously model the relation between temperature and the, say, the level of ice on the polars, that will help you to understand this. I mean, you can really try changing several parameters in the equation, in the model, and then you can really try to predict some results, results, yeah.
What area of mathematics provides the best tool for modeling?
Right now, I think it's partial differential equations, solving differential equations. Almost everything in nature, it can be modeled using partial.
Explain the connection. Why that branch of math has that?
Because, like again, almost all phenomena has a change. Either it's like for example, a motion, or like an increase in the temperature. It's the gradual increase in the temperature. These things can be modeled using derivatives.
Right.
And
so that's
basically
what that math does is measure change.
Yes.
Effectively.
Yeah.
Right. Calculus.
And the partial differential equations are
That's the key.
Yeah.
The key method. Now you talked about these problems. Can you connect your research to any of these problems, or say some other problems that need to be solved?
In general, in computational sciences, I mean, my main research has application areas, and typical application areas of my research are basically in electrical engineering. But once you have a simulation tool, a computational tool that can handle big problems, that can typically be applied with small modifications to different problems. I mean, for example, a simulator you developed for solving Maxwell equations can also be used, for example, for modeling computational fluid dynamics, for modeling fluid dynamics. I think similar things apply for modeling climate, for example. So the tools or the skills you gain for developing some tools in electrical engineering and mechanical engineering, they can be applied in modeling the changes in climate, global warming, for example. I guess that.
So what I'm hearing is that you, by developing, say, techniques for modeling the areas that you're interested in, for example, in electrical engineering and electromagnetics and so on, you can actually take that technique and use it somewhere else for something entirely different.
I would say it wouldn't exactly apply immediately. I would say it would either require some certain modifications, or the skills you learned while developing these things, they will definitely help you with the other problem.
So now I want to zero in on exactly what you are modeling. What is your area of research? And although it may be very highly technical, explain it in the simplest terms possible.
Okay. My research area is computational electromagnetics. It's an interdisciplinary field, I would say. What a researcher in computational electromagnetics does is It combines novel methods, algorithms developed in applied math. It combines he combines engineering approach, engineering models from electrical engineering, and computational resources from computer science. And the resulting product from all these combinations is, I think, new simulation tools for solving Maxwell equations. And once you have a tool in this tool in place, you can use it to solve purely electromagnetics engineering problems like radiation, electromagnetic compatibility, interference, subsurface modeling, subsurface imaging, radar applications. These are pure electromagnetics applications. Or you can use the simulation tools in multiphysics simulators, where you're supposed to model a phenomena that requires mechanical modeling at the same time, thermal modeling or electromagnetic modeling. So these simulation tools can be a component of a bigger framework.
Mm-hmm. What kind of breakthrough would be a goal for you? You know, that would really have an impact in that field.
The main purpose in this field is to try to solve more complex and bigger problems. This requires developments in different areas. The preconditioning of the methods, for example. When you have more complex systems, your systems becomes ill-conditioned, which means that the equations, the numerical equations, are not solvable. So one problem is basically to make these equations well-conditioned. So that might be one of the breakthroughs. And the other one is trying to solve bigger problems. So this will require accelerated solutions. When you have a big problem, the computation times are longer. So to enable basically solving bigger problems, you need some acceleration tools.
Mm-hmm.
And these tools are typically related to linear algebra, like matrix inversion, fast matrix inversion, fast iterative solvers are all in this group.
Mm-hmm.
So the breakthroughs in these fields are important.
Could it lead to, what would it mean, say, for Saudi Arabia to have a breakthrough that you just described?
I think one of the direct applications, one of the direct effects of a breakthrough in computational electromagnetics might be, for example, detection of oil reserves.
Mm-hmm.
I think that is really like an immediate application.
Mm-hmm.
So these simulation tools can be the algorithms developed in computationally and can be used to solve some inverse problems, where you can create images of the underground oil reserves, or it can be also water resources too.
Mm-hmm.
I think that's one of the immediate applications I can
Mm-hmm.
think of right now.
That would be highly beneficial. Can you start a company?
Yes, I mean
with those.
with some industrial collaborations and with collaboration some other faculty. I think
That's one of the goals of KAUST, of course, is to take the ideas from the lab and begin a startup, and eventually have a company that will
benefit
create a new industry, if you will.
Yes, I think that's always an option. Yeah.
And of course that doesn't speak for the fact that there may be unseen applications that could come that we don't know about at this point.
Yes, of course.
That's
I mean,
right.
there will always be, once you have a breakthrough, there is always the main result, and there's also the side, maybe smaller, but still important.
Still important and also
results.
significant.
Yeah.
Correct. How many years do you think it would take to get a breakthrough like that?
Um,
That's a tough question, of course.
Yeah, I mean,
That's a very speculative question, but you may have a goal. In fact, I hear that when you set goals, that somehow you find the means to get to them in time.
I mean, 5 to 10 years is I think is a reasonable time estimate. Yeah.
So, what advice would you give to those who might want to pursue your exact area of computational electromagnetics?
I would. I mean, this is maybe I'm repeating myself now, but
sure, that's okay, because if something is important, it bears repeating. Yeah, for emphasis. You understand? Yeah.
I mean, the important thing is really it's mathematics. I mean, you should, if you really want to be good at the computational science, not specific to electromagnetics, but any computational sciences, I think you really need to be knowledgeable in mathematics. That's one of the important issues, and the next one might be computer skills.
We stand on the shoulders of giants in science. That is, all advances tend to be tied to what great scientists have done in the past and has led up to where we are today. Who are the pioneer researchers in your field, and what was their breakthrough? I know we can start with Maxwell, but we can probably, you saw Hertz, and you can go back even earlier. So as you look at the scientists who were great in your area, and leading up to today, how would you describe them and their contributions?
I think the main breakthrough in computational electromagnetics is that happened in the 1990s, when the scientists at Yale, actually one of them is Professor Vladimir Roplin, he came up with a scheme where you can accelerate the iterative solution, for example. And this method is called fast multiple method. And this, to simplify, this method basically reduces the complexity of the solution of a linear system from order n squared to order n log n, which is mainly linear. Here n is basically the size of your, let's say, matrix, and this size it can be number of particles in a physical simulation. It can be the number of unknowns in an electromagnetic simulation, and the method he developed that it can be applied in many fields, and the computational electromagnetics has also has lots of benefits from what he developed.
Any others pioneers?
I mean, that's the most important one that comes to my mind right now.
What about your professors at you acquired your Ph.D. at the University of Illinois, Urbana? What about your professors there? Were they heavily involved in?
Actually, my professor, my advisor and supervisor, he's also actually one of the main contributors to this method. He worked with different variations, extension of this method to, for example, time domain simulations. That was his main contribution to the field.
So, explain that in simple terms. If it's possible.
The original method that has been developed was that applied to frequency simulations. So you have a time harmonic field which has a single tone frequency, and then you construct an electromagnetic system by discretizing the surfaces you have, and so that will give you like a linear system. and the method that was developed at Yale, that was applicable in those situations. But what Professor Mikkelsen, my advisor, developed was basically it was applicable to transient simulations. So in addition to the discretization in space, you also have a discretization in time. So the dimension of the problem was much higher. He developed basically a similar method to accelerate the solution of the system.
Mm-hmm. What would you consider the greatest achievement in your profession till now?
I mean, yeah, this accelerated method is one of the greater achievements. Yes.
That you have accomplished.
I developed a different variation of this acceleration method. This was one of the accomplishments I have, and the other one basically was developing a simulator which can handle different scales of geometry. For example, an example where you can use the simulator is an airplane. An airplane has different parts with different geometric scales. For example, you have the meter scale body, fuselage, and the wings. You have centimeter scale cables, and you have millimeter scale, even smaller scale circuits, micro devices.
Mm-hmm.
So the simulator I developed was basically using three different solvers. One of them was modeling the meter scale geometries. The other one, and this was a field solver, this was a Maxwell equation solver. The other one was modeling, say, centimeter scale transmission lines. This was solving the well-known telegrapher's equations. And the third and the last one was basically modeling millimeter scale or smaller circuits. This was basically a different variation of a spice solver, which is actually very well known in electrical engineering. So what I did is basically coupled these three equations in a rigorous way to end up with a more accurate solver. So this solver has many applications, but the main specific application area is basically to finding coupled voltages to cables, to analyze interference between antennas located on complex platforms like airplanes, ships, and some certain military vehicles.
Mm-hmm. I noticed that you received an honorable mention in the IEEE EMC Society in 2008. And your paper title was Fast and Rigorous Analysis of EMC, EMI Phenomena on Electrically Large and Complex Structures Loaded with Coaxial Cables. That's what you addressed.
Yes, I mean, that is the paper that just describes what I just tried to summarize.
To mention there. I also noticed that you have published quite a few papers in electronics journals and so forth. What is the key to that productivity? I mean, you have to generate a lot of data constantly in your lab to do that. It's very impressive when one publishes a lot in peer-reviewed publications.
One of the important issues is collaboration is really important. So all of these papers basically, if you notice, they have lots of people as authors.
Mm-hmm.
So I mean, while working on these projects, you basically combine powers, from different people.
Right.
So that helps a lot. That actually helps a lot to increase the productivity, because each person brings in his experience to the table, and then you basically instead of reinventing the wheel, you basically use his experience in that field. So that is one of the key issues in increasing the productivity. The other one is again working hard, spending lots of time in front of a computer and just with a pen and the paper to develop some formulations. Yeah, I guess these are the key issues.
So you bring out a point that we may have discussed earlier about the importance of teamwork in science. You know, that you cannot go it alone. That you really need to be effective within a team. Elaborate on that a little bit.
I mean, science it's a really big field. There is no way you can know everything, and you cannot have experience in everything. So I think the key point is it's really not reinventing the wheel. So if you know someone that really is experienced in his field, and if you feel like you can benefit from his experiences, you should try to go and talk to him. That's really the starting point. And then if you feel like you can have some certain common things in your research areas, but still have some differences, I think that's a really good collaboration opportunity.
Does that also relate to the reason why you came to KAUST? Because obviously this is an academic model which is interdisciplinary. And does that offer attractive features?
One of the unique features of KAUST is its research center based structure. So one research center might have researchers from different fields, and that will, I think, increase the level of collaboration. In a typical university right now, there are degree programs and people work under degree programs. Even though the collaboration efforts are encouraged, once you are, for example, surrounded with all electrical engineers, you may not really have a chance to talk to other people from different fields. But I think KAUST's research center structure will basically overcome this problem.
Mm-hmm. And then you might find new areas of research that you can.
Yes, of course. I mean, when you talk to people outside your field, it's always like a good point to start developing new ideas.
In addition to talking to people in other fields and disciplines, what do you expect to learn from your fellow computational math faculty members?
Their approach to the problems, I think they're a little bit different than engineers. I think that's one of the things I'll really benefit from, because I'm not saying it's better or worse. Their approach is different than an engineer would have.
Mm-hmm. What's the difference between applied math scientist and an engineer?
I think applied math, in general, mathematicians, they are more rigorous in formulations. They try to stay away from approximations, but I think it
that's the math.
Yes,
person,
that's the math person.
Right.
But I think it limits the applicability, and that might be one of the problems. But on the other hand, engineer has a more tendency like to simplify things. Mm-hmm. To be honest, this makes things easier to understand, and I think it increases the applicability. I mean, like applicability in the real world. That's what I'm trying to say.
What are the future goals that you have in your research career?
I'll try to actually start with developing some collaboration efforts. One of the fields I want to collaborate with is the actually applied math people here, and the other one is the Nanotechnology Center, which is not active right now, but it will be soon, hopefully. Because the immediate application of the tools I have been developing, one of the fields is basically nanotechnology, design and simulation of devices in that regime.
Molecular assemblies,
Yes.
yeah, devices that can move one atom and connect it to another atom and build.
Yes, I mean this actually this really relates to what I was telling before. I mean, the equations you develop for solving Maxwell equations can be used to simulate certain things in nanotechnology. So that might be one.
Do you see breakthroughs in nanotechnology over the next 5 or 10 years as well?
I guess things will keep on getting smaller and faster. I guess that will happen over the
The
years.
trend will be
it
continue
will continue.
in an accelerating fashion, so to speak. Huh?
Yes, I mean because the whole thing is it's like a feedback circle. Once you have faster things, then you have faster tools
Yeah.
to do more fastest things. You know, so it's really like a feedback loop.
Have you encountered the concept of singularity, something called a singularity?
Yes.
Yeah. What are your thoughts on a singularity?
You mean like in mathematical sense or?
In the sense of not of a black hole singularity, but of a machine intelligence. That is, when machine intelligence will reach the level of human intelligence. That's the term that has been described as singularity, reaching a singularity.
So I think that will be possible at some point, but I don't think it's in the near future yet. So we will still need some time for that. Yeah.
Right. Describe a typical working day for you. You know, like when you get to the lab in your office, what does a day go like for you? The reason I'm asking this question is if a young scientist hears you describe your day and something catches their attention and they say, this is the kind of day that I would love to build my career around. That's the reason I'm asking you that, because it might have some excitement in there that a young scientist out there, a potential scientist, may not know about, and you can explain that.
Like the typical day, I'm not a morning person, so I typically get up late and come to the office late, but this definitely doesn't mean that I don't work, because if you come to the office late, basically you leave late. That's actually how I prefer to do it. I mean, the typical day, I come to the office around 9, 10. I mean, the first thing you do is check your emails. And then, actually it depends. If you're teaching, you probably need to prepare for your lecture. That typically is, again, it depends. If I have notes which were prepared before, it takes like another half an hour to go over them before the lecture. But I need to prepare them from scratch. I start earlier, like.
How much time do you spend preparing the average lecture, say from scratch?
I mean, I think if the lecture is around like an hour, to fully prepare the lecture notes and think about how to present them, I think it will take 2-3 hours, 4 hours maybe for like an hour lecture.
Prepare the handouts and all of that.
Yeah. Yes.
Right.
So that's some part of the day, and in the remaining parts you talk to people. Some of these people are probably the ones you're already collaborating with some certain projects, so you exchange some ideas with them. You see how the things are progressing, improving. With some people you're starting to work on certain projects, so it's really like brainstorming. And if you have students, you typically follow their progress.
Yeah. That's what I was going to ask. How much time do you spend with your Ph.D. students? On average, daily, you know.
Actually, this is the first time I'll be dealing with PhD students as a professor. As a postdoc, I also supervise some 2-3 graduate students. It really depends on the student and your interaction with him. But typically, I would say the average number is like 1 to 2 hours per day.
Per student.
Per student, yeah.
That takes up a lot of your time.
Yeah, again, it really depends on the student. Some of the students, they like to be independent.
Right.
So you really don't try to interfere with their work. So you just supervise them and then give them.
Do you end up working in the lab with them, or are they just giving them direction so that they go back to the lab?
As a postdoc, it's basically I was more working with them.
Hands-on.
I was more hands-on.
Yeah.
But I think one thing a professor should do is basically try to a little bit stay away from the hands-on work, because the main idea behind the mentor-student relation is basically try to raise someone that can be an independent researcher.
Mm-hmm.
So I think the student has to really feel that, you know.
What would your lab look like? What kind of instrumentation you would have in your lab, and what kind of experiments do you do?
I don't really do experiments.
Mm-hmm.
It's all simulations and developing codes. So I have a really simple lab.
So it's a computer, essentially.
Yeah.
Computer workstation.
I have a desktop. Or a laptop.
Sure.
Both will work. And I typically use this as a client to connect to a bigger computer like Shaheen here, or some other Linux Unix clusters. So that's.
And you have special software on your computer as well as on the big computer like Shaheen?
It really depends on the work I'm doing. I mean, the simulation tools I developed, they are basically the codes are written from scratch, so they don't require any commercial software. It's just a compiler.
So for example, on a typical simulation that you might run, how many lines of code would that involve?
The work I just described to you before about the hybrid simulator.
Cables.
I think the cables, circuits, and the field solver. That code I think is around 20,000 to 25,000 lines.
And you wrote all of that?
Yes, but that was over I think master's plus PhD, so that was over 5-6 years.
5-6 years. So is that software you can commercialize?
Actually, yes. We were working on a proposal together with a company in the United States. The first customer was Air Force. So we were trying to put an user interface on the simulator with the company. And once that is not in place yet. I mean, some parts of it are in place, but once the first step is done, the company was also planning to reach to regular customers, not like special customers like the.
Sure. So, sort of commercial. Customers who might be able to benefit from that.
Yes.
But so your work involves being a software writer as well as that's an integral part of your work. In fact, right.
I mean, scientific tools. I mean, the typical scientific tool in academia, it doesn't have user interface. It doesn't have fancy looking things. So the main idea is basically developing the algorithm.
So you have to create your own tools to accomplish your goals. You know, like a lot of scientists, they have all these other tools that they use to generate their data. Before you can generate your data, you have to make your tool first. You know?
Actually, the purpose is to make the tool. Yeah. So that's really the enabling.
That is actually the heart and soul of what you do, making the tools.
Yes.
And then you run the tools to test out
so basically
the algorithm.
What you try to do is to come up with the fastest and the most accurate algorithm.
Okay, so that 25,000 lines of code, is that considered one big algorithm? Would that what it would be?
It is different. I would say combination of several algorithms.
There's multiple algorithms built in it.
It's not a single.
So define an algorithm.
You mean like specifically, or?
Yeah, because I'm thinking about our audience now. They might not know what an algorithm is. What is an algorithm?
I think it's a methodology you develop for solving a certain problem. I mean, this is the most general definition, I think. I mean,
Okay, a method for solving a problem.
Forming a certain problem.
Okay. And it turns out that there's a building at KAUST that's named after the father of algorithms. Isn't that correct? Al-Khwarizmi.
Yes.
Right. And he's a mathematician dating back quite a few centuries, of course. Okay, we're getting close to the end here. Did you finish describing that typical day? You got into the afternoon.
Yes.
And then anything?
Yeah, I mean,
You said you would be going late. So what would happen later in the afternoon?
What happens is actually after evening, many people leave, so it gets quieter in the office and in the building, and I think it's really easier to work in that environment. So
would you consider that your thinking time?
Yeah, I think
when things got quiet.
Yes, I think that's really late.
How important is that for a scientist to have thinking time?
I mean, it is important because you are supposed to come up creative solutions to certain problems, and that wouldn't be possible without basically having some thinking time. I would suggest like a typical time you should just focus on certain ideas. Should be like maybe an hour, 2 hours a day. And most of the time actually that's difficult because I mean you really, your day is really full of
interruptions and so on. Yeah.
So actually that's one of the reasons why I try to stay late. When people leave, it's really easier to focus on certain things.
Right. Do you feel that kind of thing is critical to the creative process and innovating, coming up with a new idea?
It's one of the critical components. But again, to repeat myself, I'm repeating myself, but the other component is really is to never give up.
Right. Well, I see that that's a theme in your thinking, never give up. And I think that's a really great message for a young student, to hear that, because we have that tendency of observing students who give up a lot. And when they hear you, a highly successful scientist and professor who really has benefited from that philosophy, then they can also benefit from that same philosophy. I'm going to get away from science a little bit and talk about the fact that you have many other things that will create balance. What are some of the hobbies that you pursue?
I try to exercise. I like playing squash, for example. I used to do some biking, road biking in US. At some point, I'm not doing it anymore, but I used to play chess. That was, I think, between high school and college. And it's, I mean, I try to read books, but I mean, I don't count reading technical books as a hobby, but I try to read sometimes more relaxing novel type
leisure reading.
Leisure reading,
Right,
yeah.
right.
I try to do that as much as I have the time.
That's right. And do you have a family that you have here with you in Saudi Arabia?
I'm single.
Oh, okay. So that is a future
Yeah,
possibility.
yeah, I guess so.
Sure. So obviously, when you have these other things you do in addition to your work, it creates a kind of a balance which is good for even being more productive in your work, in a sense.
Oh,
Because
yeah,
it takes you away from it for a while, and then you can come back to it.
Yes, I mean, no, I think taking a break is it's important. I mean, because the whole process is actually it's exhausting. I mean, you cannot continue doing it for long periods of time without taking breaks.
How many hours a day do you think you average in your work?
I typically sleep like 7 hours a day, and I think I'm spending time at the office maybe 12, 13, sometimes 14 hours a day.
That's long day, and
Yeah.
and that gives a student out there an idea of what it takes. You know, you don't punch a clock, but you're there because it's interesting, and
Yes,
you
yes.
find it the place where you're having the most fun, so to speak.
Yeah, I mean, that's one of the things I try to emphasize actually. You should really like what you're doing. I mean, if you don't, it's really difficult to be successful because you'll be forcing yourself to work on it, you know. But if you like it, it will come naturally. So you'll really want to work on it. You'll want to spend time on it, you know. And that is really the key to success.
Professor Hakan Bagci, thank you very much for
Thanks a lot.
a great interview.